We have learned modular exponentiations and its security vulnerabilities. Today we are going to talk about how to fix these security vulnerabilities from algorithm perspective. And this approach is called randomized modular exponentiation. We know in modular exponentiation, our goal is to compute x to the power d mod n, and we know the attacker's goal is trying to find the value of the exponent d. And the most popular implementation of this is called square and multiply algorithm, and we have seen the vulnerabilities in that algorithm. And in the randomized modular exponentiation algorithm, there are several steps. First, we will choose three random numbers, R1, R2, and R3. And then we are going to change the three important numbers x, d, and n in the modular exponentiation to x prime, d prime, n prime, following the following formulas. X prime equal to x plus R1 times n. D1 equal to d prime equal to d plus R2 times phi of n. Phi is the Euler's phi function, which we are going to define next. N prime equal to R3 times n. And then, instead of computing the modular exponentiation of x to the power d mod n, we compute x prime to the power d prime mod n prime. And we call this result y prime. And after this, we do a modular y prime mod n, and we call the result y double prime. The claim we have here is this y double prime is the same as y, which is the modular exponentiation we are trying to compute. Let's first do a quick review of the square and multiply algorithm for modular exponentiation, and then see what is the vulnerability here. And the example we have here is we want to compute 15 to the power 47 mod 26. The first step is to convert the decimal number 47 to binary. And here's the standard procedure how to do the decimal to binary conversion. We divide 47 by 2, the quotient is 23 and has a 1 as remainder. And then we divide the quotient 23 by 2 again with a new quotient 11 and a remainder 1. And then we keep on dividing the quotient by 2 and then get the new quotient, get a remainder, and then keep on doing this. 5 divided by 2 equal to 2 with 1 as a remainder. And 2 divided by 2 with 1 as the quotient, and there's no remainder. And finally, 1 divided by 2 with 0 as quotient and 1 as remainder. And then we stop. So now with all these remainders, we try to write these remainders from bottom to up, bottom up. And then this new sequence is the binary representation of 2. Let me repeat again. So to convert a decimal number, 47 in this case, to binary, all we need to do is keep on dividing 47 by 2, get a quotient, get a remainder, and then keep on dividing the quotient by 2, get a new quotient, and then keep on doing the division. And then we keep track of all the remainders and write down them backwards from the last one to the first one. And this is the binary number for binary equivalent of 47. Now we use the left to right square and multiply algorithm to compute 15 to the power 47 mod 26. We first write down the binary representation of 47, start from the leftmost bit 1, 0, 1, 1, 1, 1. Remember when we do this square and multiply algorithm, and when we move from one bit to another bit, we square the current value we have, and then once the bit is a 1, we do a multiply by 15. So we start with 15, and we do 15 squared because this is 0, so we don't do any further multiplication. 15 squared is 225, or modulo 26, this is negative 9, or it is positive 17. Next, we do a square of negative 9, and because the bit is 1, so we multiply this by 15. The square of negative 9 is 81. 81 mod 26 is 3, because 78 divided 26 equal to 3. So 3 times 15 is a 45, and double 26 is 52, so 45 is 7 away from 52, so 45 equal to negative 7 mod 26. So next we have another 1, so we square the negative 7 we have as I multiply by 15. This gives us 49 times 15. 49 mod 26 is a negative 3, and negative 3 times 15 is negative 45. And because 45 mod 26 is negative 7, so negative 45 mod 26 must be positive 7. And we keep on doing this. Square the 7 here and multiply by 15 because the bit 1, so we got 49 times 15 again, which is 7. And we do this again, so eventually we know that 15 to the power 47 mod 26 equal to 7. However, we have pointed out there is a vulnerability in this calculation, because whenever the bit is 1, we do one step, which is the multiplication. And if the attacker, they can monitor the set channel information, they can figure out this extra step and then reveal what is the secret key here, or the value of the exponents. Before we talk about how to fix this with the randomized modular exponentiation, we are going to introduce the Euler's phi function as we have promised. Euler's phi function is actually the number of positive integers less than or equal to n and relatively prime to n. And this stands for the great common divisor between k and n is 1, which means they are relatively prime to each other. We'll see a few examples here. So first, phi of 2, there's only a number 1, which is relatively prime to 2, so phi of 2 equal to 1. For 3, we know both 1 and 2, they're relatively prime to 3, so phi of 3 equal to 3. Phi of 5, all the numbers less than 5, 1, 2, 3, 4, 5, 4, they are relative prime to 5, so phi of 5 is 4. At this point, we can reasoning that for any prime number p, phi of p should be p minus 1, because all the numbers from 1 to p minus 1, they are relatively prime to p. Next, we see phi of 10, and we see number 1, 3, 7, and 9. These are the 4 numbers that are relatively prime to 10. So phi of 10 equal to 4, which happens to be phi 2 times phi of 5, which is 1 times 4. And the last example is phi of 15. So we know 3 is not relatively prime to 15. 5, 6, 7, 9, 10, 12, and 15. Those are the numbers that are not relatively prime to 15. These remaining numbers, they are all relatively prime to 15. And if we count this, we have 1, 2, 3, 4, 5, 6, 7, 8 numbers, which happens to be the product of phi of 3 and phi of 5. So for these two observations here, it happens they are not a coincidence. Indeed, we have this formula here. So if we have two numbers, m and n, they are relatively prime to each other, and so phi of m times n equal to phi of m times phi of n. Actually, to prove this is fairly straightforward. So we first count how many numbers between 1 and n times m are not relatively prime to n times m. So from 1 to m, there are m minus phi of m numbers that are not relatively prime to m from the definition of phi of m. And for each of these numbers, and if they multiply by n, all these numbers, they multiply by from 1 to n, and the product will not be relatively prime to m times n. So these are the numbers that will not be relatively prime to m times n. And for the numbers between 1 and m that are relatively prime to m, if the second number, which are not relatively prime to n, their product will not be relatively prime to m times n. It follows the similar argument as the first term. So if we multiply this, and then we see the phi of m times n with a minus, and phi of m times n with plus, these two terms, they cancel each other. So what we have is m times n minus phi of m times phi of n. So these are the numbers between 1 and m times n that are not relatively prime to m times n. So the number that are relatively prime to m of n will be m times n minus this quantity, which happens to be phi of m times phi of n, which is what we have claimed here. To see a concrete example, we consider phi of 10. So phi of 2, which is one number, 1 here. Phi of 5, which is 4, contains the number 1, 2, 3, and 4. So for the numbers that are not relatively prime to 10, from the first term, we have 1 here, and this one can be multiplied by all the numbers between 1 and 5. So we have this 2 here, which is not relatively prime to 2. 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. These are the 5 numbers that are not relative prime to 10. And for the second term, for the phi m, which is this one here, and n minus phi of n, in this case, there's only one number, which is 5, not relative prime to a 5. So we get the number 5 here. So in total, we have 1, 2, 3, 4, 5, 6 numbers that are not relatively prime to 10, which tells us phi of 10 equals 10 minus 6, which is 4. Indeed, we have the Euler's product formula, which we're not going to give the proof. It says that if we can do the factorization of n equal to p1 to the power k1 times p2 to the power k2 times etc. to pm times to the km, where all these pi's, p1, p2 until pm, they are distinct prime numbers. If we have this prime factorization of n, Euler says phi of n equal to n times 1 minus 1 over p1 times 1 minus 1 over p2 times dot 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 until 1 minus 1 over pm. The next important thing about Euler's phi function is the one called Euler's theorem, which happens to be one of the most elegant theorem in number theory. So it says when we have two numbers, a and m, they are relatively prime to each other, and then we have this phi of n, which is the phi function. It says a raised to the power phi of n mod n equal to 1. And let's see one very simple application of this Euler's theorem. So let's see, we want to find the modular multiplicative inverse. If we have n and m, a and n, they are relatively prime to each other. From Euler's theorem, we claim that the modular inverse of a, which is a negative 1, equal to a of phi n minus 1. And to see this is relatively easy. So when we do a multiplied by a to the power phi n minus 1, this gives us a to the phi n. And followed Euler's theorem, this tells us this is 1. So we see a times a to the power phi n minus 1 equal to 1 mod n. That is exactly the definition of modular inverse. To see an example of this, we know 7 and 10, they are relative prime to each other, and we have seen phi of 10 equal to 4. From this, we know that the modular inverse of 7 mod 10 is indeed 7 to the power 4 minus 1, which is 3. So 7 cubed is 7 squared, which is 49 times 7. 49 mod 10 is 9, so it is 9 times 7, which is 63, and modular 10, mod 10 is 3. And to verify this, we see 7 times 3 equal to 21, which mod 10 is 1. So now we have all the necessary background we need to learn the randomized modular exponentiation. So let's first see an example, see how it works, and then give a formal proof of this. So this is the procedure to do the randomized modular exponentiation, where we select the 3 random numbers. So in this case, let's pick R1 equal to 4, R2 equal to 7, and R3 equal to 5 randomly. Following the definition of x prime, d prime, and n prime, we can compute these quantities. By the way, phi of 26 equal to phi of 2 times phi of 13, which is 12. So x prime equal to x, which is 15, plus R1, which is 4, multiplied by n, which is 26. This gives us 119. D prime equal to d, which is 47 here, plus R2, which is 7, times phi of n, which is 12. So this is 47 plus 81, give us 131. Finally, n prime is defined as R3 times n, so in this case 5 times 26 is 130. So now we can compute the modular exponentiation. Instead of doing 15 to the power 47 mod 26, we compute 119, which is x prime, to the power of d prime, which is 131, and mod n prime, which is 130. So again, the first step is to convert 131 into binary. So this is the procedure as we have outlined earlier, and I'm not going to go through the details again. And we do the keep on divided by 2 and record all the remainders and then write them bottom up, so we get the binary representation. And then we can use the left to right square and multiply algorithm to compute and find out 119 raised to the power 131 mod 130 is indeed 59. And now we follow the last step to do a mod n, which is 26. So 59 mod 26 is 7. And what we see here, this is the same 7 as we have computed earlier. So when we take a look at this, we do compute a modular exponentiation during this procedure. However, this modular exponentiation, the attackers may see some information about 131, and from this they cannot get much information about the secret D here, which is 47. Let's now give a formal proof of the randomized modular exponentiation to show its correctness. So let's see, we have two numbers a, which is equal to c mod p. So we can write a as c plus p times the integer k1. And similarly, if b equal to d mod p, we can write b as d plus p times k2. So the product of a and b can be written as c plus p times k1 times d plus p times k2. And if we break the parentheses, and when we do the mod operation of mod p, all these terms disappeared except cd, which means if a and c, they are equivalent mod p, b and d are equivalent mod p, and then their product a times b will be equivalent, will be the same as c times d mod p. So now let's see the modified or randomized modular exponentiation x prime to the power d prime. So when we plug in the definition of x prime, which is x plus r1 times n, and the definition of d prime, which is d plus r2 times phi of n, so we get this equation here. And then once we separate the exponents, we get the first term times the second term. So let's denote the first time with a, and then let's do a mod n prime operation here. So if a equal to x plus r1 times n to the power d mod n prime, we can write a equal to this plus n prime, which is r3 times n times the integer k1. And if we mod n of this quantity, we see this term disappeared after mod n. And for this binomial exponential, but following the binomial equation formula here, for this term, when we do a mod n, the only thing remaining will be x to the power d. For the second term, let's call them b, which is x plus r1 times n raised to the power r2 times phi of n mod n prime. And so b can be written as this plus n prime, which is r3 times n times k2. And if we do a mod n operation, so this term disappeared, and for this term, and because we do mod n, so the only thing left is x to the power r2 times phi of n. So now because of Euler's theorem, we know this x to the power phi of n mod n equal to 1. So eventually what we get here is x double prime will equal to x prime to the power raised to the power d prime will equal to a times b, and a will be x to the power d times b, which is 1 mod n. So this eventually is x to the power d, which is y mod n. So this shows that the randomized modular exponentiation gives the correct answer of the modular exponentiation x to the power d. However, the secret, which is the exponent d, will be hidden. The modular exponentiation we are doing here is x prime to the power d prime mod n prime.